In this module, we're going to look at hypothesis tests for one population mean. And before we even get into that, we're going to look at different ways to do hypothesis testing, including the critical value approach and the p-value approach. The reason we use inferential statistics is so that we can make a decision about the value of a parameter like a population mean. And one of the most commonly used methods for making such decisions or judgments is called the hypothesis test. A hypothesis is simply a statement that something is true, or it's something that you can test. And we'll focus on hypothesis tests with two different hypotheses, and that is the null and alternative hypothesis. With the null hypothesis, which is denoted as H sub 0, this is your hypothesis to be tested, and it's always stating no difference, no difference, no difference. So generally, this is a statement that a population parameter has a specific value, and it's our starting point for investigation. Now, the alternative hypothesis is a statement about the same population parameter used in your null hypothesis, but we're going to say that the population parameter is different in some way, and we always denote it as an H sub A. Originally, the word null in null hypothesis really stood for no difference, or the difference is null. But of course, over the years, null hypothesis has come to mean simply a hypothesis to be tested. So these are the definitions for our null and alternative hypothesis and the hypothesis test. A null hypothesis is a hypothesis to be tested, and we use the symbol H sub 0 to represent the null hypothesis. An alternative hypothesis is a hypothesis to be considered as an alternative to the null hypothesis. We use the symbol H sub A to represent the alternative hypothesis. And a hypothesis test is the problem in a hypothesis test is to decide whether the null hypothesis should be rejected in favor of the alternative hypothesis. And we can do some practice on these with some, examples. So skip the dishes orders in Medicine Hat takes too much time to be delivered. And if your null hypothesis is no change, no change, no change, then our null hypothesis here is that the dishes are slow. It comes slow. But the alternative could be that they actually come faster than what we originally thought. Vaping will impact the quality of your life. So the null hypothesis here is that vaping doesn't have an effect on the quality of your life. And then alternatively, we could say it makes your life worse or it makes your life better. And finally, low-fat recipes are just not as tasty as regular fat. So the null hypothesis here is that there's no change, no change. Low-fat recipes just aren't that tasty. And then you could compare it to alternative hypothesis, like low-fat recipes are actually tastier than regular fat. But let's really break it down into how you would go about choosing the hypothesis. So for this course, the null hypothesis for a hypothesis test concerning a population mean always specifies a single value for that parameter. So we can always express the null hypothesis as mu is equal to mu sub 0. The alternative hypothesis is talking about if the primary concern is deciding whether a population mean is different from a specified value or if it is greater or less than. So for the null hypothesis, always ask yourself, is the population mean different? And then you can write it out as such. The population mean is equal to the mean of the parameter, or it is not equal. And we call that a two-tailed test. And this will make more sense as we move forward. If the primary concern, however, is deciding whether a population mean mu is less than a specified value of mu sub 0, we express the alternative hypothesis as such, mu, and then we'll have the less than symbol, and then we'll have the value of the parameter here. And a hypothesis test whose alternative hypothesis has this form is called a left-tailed test. And you know it's left-tailed because it's pointing to the left. So keep that in mind as a quick tip. If, however, your primary concern is deciding whether a population mean mu is greater than a specified value of mu sub 0, we express the alternative hypothesis as mu, and then we've got the greater than symbol, mu sub 0. And a hypothesis test whose alternative hypothesis has this form is actually called a right-tailed test. And you'll know that it is a right-tailed test because it will point towards the right. In this example, decide on the null and alternative hypothesis. The bookstore is selling your textbooks and you want to know if the mean retail price for business books this year has increased from last year's mean retail price of $80. So your null hypothesis in this case is always going to be, and I mean in this case, I mean for this course, is always going to be no change, no change. So the null hypothesis is that the last year's book price is equal to this year's book prices, whereas the alternative hypothesis is saying that the price is greater this year. So mu is greater than 80, and so this is a right-tailed test because a greater sign would appear in the alternative hypothesis. Let's do some more examples of this. Let mu denote the mean height of today's women in their 20s. The null hypothesis is that the mean height of today's women in their 20s equals the mean height of women in their 20s half a century ago. So that is stating that h sub o is mu is equal to 62.6 inches tall. Now, the alternative hypothesis is that the mean height of today's women in their 20s is greater than the mean height of women in their 20s half a century ago. So that would make it h sub a mu, and then you would have the greater than symbol to 62.6 inches. And so let's write that out so that we know for sure that we're on the same page. So if I go HA, and what I want to do is I want to say that mu, like a giant U, is greater than 62.6 inches. And so you can see with the greater than symbol that I have here, it is pointing to the right. And that's how we know that this is a right-tailed test. So after you decide on your null and alternative hypothesis, what you'll need to do is run some sort of a statistical test. And at this point, we'll just call it a test statistic, a statistic calculated from the data that is used as the basis for deciding whether we will reject the null hypothesis or not reject it. And this is the logic behind the hypothesis test. You take a random sample from the population, and if the sample data are consistent with the null hypothesis, you don't reject the null hypothesis. If the sample data are inconsistent with the null hypothesis and supportive of the alternative hypothesis, then you reject the null hypothesis in favor of the alternative hypothesis. And what you need to note here is that we're never like accepting anything. We're just saying that we will reject the null hypothesis or fail to reject the null hypothesis. Any decision we make based on a hypothesis test might be wrong because we've used maybe partial information obtained from a sample to draw conclusions about an entire population. And so there are two types of incorrect decisions that we can make. And so we'll call them type 1 and type 2 error. In type 1 error here, you reject a null hypothesis that ends up being true. And in your type 2 error, what you do here is you do not reject a null hypothesis, and it is false, and that is our type 2 error. So again, type 1 error is rejecting the null hypothesis when it is true. Whereas type 2 error is not rejecting the null hypothesis when in fact it is false. And here is that chart again, where it's showing where you would get a type 1 versus a type 2 error. This here is a flow chart, and it is showing all of the different pathways you can take for making a decision. So you start with it and you'll have a null hypothesis. Is it true? Yes. Then you'll go HO rejected. Yes, type 1 error. But is it true? Yes. Is the HO rejected? No. Then you've made the correct decision. So you're never really going to have to use this flow chart, but just in case you wanted to go through it to help get to the idea of type 1 and type 2 error in your mind, I've put it in here for you. Let's look at an example. Consider a pretzel packaging hypothesis test. The null and alternative hypotheses are shown below. So in our null hypothesis, mu is equal to 454 grams, and that's stating that the packaging machine is working properly. Whereas your alternative hypothesis is that the mu is not equal to 454 grams. That means the packaging machine is not working properly. Explain what each of the following would mean in this context. So let's go through it. Type 1 error. A type 1 error will occur when a true null hypothesis is rejected. So in this case, a type 1 error would occur if, in fact, mu does equal 454 grams, but the results of the sampling led to the conclusion that it doesn't equal 454 grams. Now, what about a type 2 error? A type 2 error will occur when a false null hypothesis is not rejected. So in this case, a type 2 error would occur if, in fact, mu did not equal 454 grams, but the results of the sampling fail to lead to that conclusion. And what about a correct decision? Well, this can occur in two ways. A true null hypothesis is not rejected, and this would happen if mu was equaling 454 grams and the results do not lead to the rejection of that fact, or a false null hypothesis is rejected. This would happen if, in fact, mu did not equal 454 grams, and the results of the sampling actually did lead to that conclusion. So one of the ways we can tell if a hypothesis test is effective is by analyzing the chances of making an incorrect decision. And so a type 1 error occurs if a true null hypothesis is rejected, and the probability of that happening is called a type 1 error probability, commonly called the significance level of a hypothesis test. And you guys have seen it, and it's been denoted as alpha, the lowercase Greek letter. Now, a type 2 error occurs if a false null hypothesis is not rejected. And the probability of that happening, the type 2 error probability, is denoted with a B or beta. It's the lowercase Greek letter beta. So ideally, in a perfect world, both type 1 and type 2 errors should have really small probabilities, and then your chance of making an incorrect decision would be really small regardless of what the null hypothesis is true or false. But that can't always happen, and so we do have to balance our significance level alpha with our beta, B, and also with our sample size. And this leads to the key fact on the relation between type 1 and type 2 error probabilities. For a fixed sample size, the smaller we specify the significance level of alpha, the larger will be the probability beta of not rejecting the null hypothesis. So the significance level of alpha is the probability of making a type 1 error, and that means rejecting a true null hypothesis. If a hypothesis test is conducted at a small significance level, the chance of rejecting a true null hypothesis will be really small. So we'll generally, when you're doing these things, you'll generally get a small significance level, and then we can evaluate the outcome from there. But we usually do not know the probability for beta of making a type 2 error. And that is, of course, not rejecting a false null hypothesis. And so consequently, if we do not reject the null hypothesis, we simply are just reserving judgment about which hypothesis is true. So if we do not reject the null hypothesis, we conclude only that the data do not provide sufficient evidence to support the alternative hypothesis. And so there's only kind of two ways you can possibly conclude on these hypothesis tests. If the null hypothesis is rejected, we conclude that the data provide sufficient evidence to support the alternative hypothesis. And if the null hypothesis is not rejected, we conclude that the data do not provide sufficient evidence to support the alternative hypothesis. Not that we have sufficient evidence. So we're never accepting anything. We are just simply supporting or not supporting based on evidence. A lot of that information is stuff you just have to put into practice to fully understand it. So don't worry too much about the definitions and such, and we'll go on from there. And once you start putting it into practice, it will make a lot more sense. So we have a hypothesis, we have a null and alternative hypothesis. How do we decide to reject or not reject a null hypothesis? Well, we do that by comparing a value for a test statistic. So you're calculating some sort of statistic, and then you're using that number to make a decision about your null hypothesis. And there are two approaches that we're going to look at. One is called the probability approach, or the p-value approach. You may have heard of it. And the other one is called the critical value approach. First, we'll start with the critical value approach to hypothesis testing. With the critical value approach, we choose basically cutoff points based on the significance level of the hypothesis test. So the criterion for deciding whether to reject the null hypothesis involves a comparison of a value of a test statistic, so something you calculated, to cutoff points. And I'm going to show you how you can get those cutoff points. So let's look at some definitions for the critical value approach before we move forward with it. So first of all, we've got the rejection region, we've got the non-rejection region, and we've got the critical value. And you can see that we've got a picture here of a normal distribution. And I find that drawing these out actually will really help you in making a decision on whether you would reject or fail to reject. So what is the rejection region? It is the set of values for the test statistic that leads to rejection of the null hypothesis. And so you can see here that we've got the rejection region here highlighted in blue. The non-rejection region is the set of values for the test statistic that leads to the non-rejection of a null hypothesis. And you can see that is on the other side here, and it's not filled in blue. But how do you know where the rejection region starts and the non-rejection region starts? So that's based on your critical value. The critical value is the value or values of the test statistic that separate the rejection and non-rejection region. It is also part of the rejection region itself. So negative 1.645 is within the rejection region itself. And this is a graphical display of the rejection regions for two-tailed tests on this side, left-tailed, and then right-tailed tests. So for a two-tailed test, the null hypothesis is rejected when the test statistic is either too large or too small. And the rejection region for such a test consists of two parts. There's one on the left-hand side and one on the right-hand side. So if your number, your test statistic, falls within here, you do not reject HO. So for example, say that this tick right here is 1, it represents 1, and say this represents 2 and this represents -2. Well, if you've got a number that is in 1, all the way from 1.00 to 1.999, it's going to be in the non-rejection region. But if you get up to 2 or -2 down here, you reject your HO. And what number are you using for that? The test statistic you calculate. Now for the left-tailed test, the null hypothesis is rejected only when the test statistic is too small, and the rejection region for the test consists of only one part on the left. Whereas the right-tailed test, the null hypothesis is rejected only when the test statistic is too large, and so the rejection region for such a test consists of only one part on the right-hand side. And this table here is just showing the rejection regions for the two-tailed, left-tailed, and right-tailed tests. So of course with the two-tail, it is both side, and then of course we've got our signs either pointing to the left or pointing to the right. Okay, so we know that we're going to get some sort of a test statistic, and then we're going to have to compare it to some sort of a value to decide whether it is in the rejection region or not. And that value is our critical value. So obtaining critical values. Suppose that a hypothesis test is to be performed at the significance level alpha. Then the critical value or values must be chosen so that if the null hypothesis is true, the probability is alpha that the test statistic will fall within the rejection region. And so again, we're going to have to put this into play for you guys to really understand how it is. But with the critical value approach, we reject the null hypothesis if and only if the test statistic is going to fall within that rejection region. Obtaining critical values for a one-mean z-test. So this procedure is used to perform a hypothesis test for one population mean when the population standard deviation is known. And this is the first hypothesis test that we're going to look at. Now you've already done the confidence interval procedure for this, and now we're just moving into the hypothesis testing procedure so that we can obtain those critical values. So in this test, we've got our null hypothesis is mu is equal to mu sub 0, where mu sub 0 is some number. The one mean z-test provides test statistics that tells you how many standard deviations the observed mean is from the population mean. And the formula for this test is shown right here and is also on your formula card. Okay, so now that we've looked at the anatomy of the one mean Z test, let's look at how we obtain the critical values for the one mean Z test. So in this example, it says determine the critical values for a one mean Z test at the 5% significance level, which is alpha is equal to 0.05. And we're going to do that for if the test is two-tailed, left-tailed, and right-tailed. So let's walk through that. All right, so how do we get those critical values? Well, our alpha is 0.05. This was given to us in the question. It might say a 5% significance level, and that's what it translates into. So if we want to find the critical regions for a two-tailed test, what we have to do is realize that the rejection region is going to be both on the left and the right side. So critical values are the two z-scores that will divide the area under the standard normal curve into a middle 0.95 area with two outside areas of 0.025. So this is going to be plus or minus z is 0.025. Now this is where you're going to want to go and grab your table too. So it's going to be important that you have these tables available for you, ready to go. So if we take 1 minus 0.025 and we look in the body of the table, so if you take 1 minus 0.025, you're going to end up with 0.9750. Look in the body of the table and then translate that over to the first column and go up to the first row, and you are going to get a value of plus or minus 1.96. So that means on the left-hand side it's negative 1.96, and on the right-hand side it's positive 1.96. And so this makes those critical points to say if your number is below 1.96 but higher than negative 1.96, you will not reject your HO. Now for the left side, the rejection region is to the left, and the critical value is the z-score with the area 0.05 to its left under the standard normal curve. So that means it's going to be z 0.05, but since it's the left, we know it's negative. So of course you can do the same thing. You can, take your 1 minus 0.05, and then you're going to get a number, and you will look in the body of the table for that number, and what you'll find is that it falls equally between two different z-scores, so 1.64 and 1.65, and so you take the average of it and you get negative 1.645. And so that means that any value that is less than negative 1.645 is rejected, but anything higher than that is not rejected. And then it's the same for the right-hand side, except for you're just taking away that negative essentially here. So the critical value is the z-score with the area 0.052. It's right under the standard normal curve. So we already did practice on this kind of stuff earlier on when we started in the normal distribution, and we were talking about all of the different types of tables, and that's why it was important back then to learn that so that you can apply it now. And this is likely already on your formula card, and if it's not, you can write it on there. I don't mind. These are some of the important values of Z alpha that you'll come across, and they, like I said, we use the same ones kind of over and over again because we're always looking at 5%, 10% significance values like that. And so these are some of the values that are translated over. Now, when you see the Z alpha 0.05 and then the Z alpha 0.005, we've got more decimal places here, and that's because it was an average between two of them. So let's go through the general steps for the critical value approach. Sometimes you'll see this as the traditional approach or the classical approach, and there are 6 major steps here. So the first step is to state the null and alternative hypothesis, and this will help you to recognize if this is one or two-tailed, and then you will decide on the significance level alpha. Usually that will be given to you in the question, and then you'll compute the value of the test statistic, whatever that happens to be. 50, and then you'll determine the critical values. Finally, you'll take the test statistic and compare it to your critical values, and if the value of the test statistic falls within the rejection region, you reject HO, otherwise you do not reject HO, and then obviously you have to interpret the results with a sentence to conclude. So let's do an example. A Boeing 737 aircraft has a lot of problems with it, and it had to be recalled. So there's lots of evidence of flights that have gone down because of these planes. One weakness was the breakage of the rivets, and I had to look up what a rivet is, and it's basically like a giant, huge screw. So that's not a good thing on an airplane. So the new specifications state that the mean shearing strength of all such rivets, mu, has to be at least 925 pounds to make sure that we are safe. So let's write out our null hypothesis. It's going to be that mean, or the population mean, is equal to 925 pounds. So it's at least 925 pounds, no change, no change, no change. Now, the problem is, though, is that anytime we get rivets that have a mean less than 925 pounds, we see aircraft accidents. So our alternative hypothesis here is that the mean is less than 925 pounds. And we're going to use an alpha of 0.05, which translates to a 5% significance level. If you're not given alpha, just assume it's 0.05 because it is the most statistically used one that you'll get. So a random sample of 50 rivets is selected, so n equals 50, and each rivet is tested, and the sample mean shearing strength is calculated. So we've got an X bar of 921.18 and an N of 50, and we can do the one mean Z test to get a test statistic so that we can then decide whether we are going to reject or fail to reject this. So this would happen if you were looking at a bunch of different rivets at a manufacturing place and you needed to take a sample of data to make sure that everything is looking good. So what you can see here is I've got Z star. What you'll find is that when you're actually putting a hypothesis test into action, they will put an asterisk beside it to denote that it is a test, like we're doing a one mean Z test. So we're going to, and you should pull out your formula card so that you can see the original formula here. But what we've got here is X bar minus mu, which is 925, we know that from here, divided by 18 over the square root of 50. And with the 18, there's not, you guys wouldn't have known where to get that from. I'm just going to tell you that this is what we're going to use for it, the standard deviation here. All right, so we calculate all of this and we get a test statistic of negative 1.50, but that means relatively little to us unless we can use it to make a decision. Okay, so let's find our critical value. And again, you're going to want to use your table 2, your areas under the standard normal curve. So what pieces of information do we need to do that? Well, we need to know our alpha of 0.05. So we had stated in the question that alpha was going to be 0.05 or 5%. And then what we want to do is take 1 minus, I'm just going to see if I can get my pen working, 1 minus 0.05. So you can take that information and go 1 minus 0.005. And again, you guys are going to start to memorize these things because you use them so often in statistics that you actually won't have to calculate some of these things. I mean, do you already know? You probably do. Okay, so 1 minus 0.05 is 0.95. Then we want to go and do 0.95 in the body of our table. And when you go and you look at 0.95 in the body of your table, you're going to find two numbers that are equally far apart. So you're going to get 0.9. I just want to write out the exact numbers, 9495. And you're also going to find the 0.9505. 0.9505. Okay, and so these translate to 1.64 for a Z-score and 1.65. And so you add those together and divide it by 2. You take the average of them, and you will end up with negative 1.645. Now, of course, when you have a left-tailed, you automatically know it's going to be negative. And if it's on the right-hand side, then it's going to be just the positive version of this. So our critical value here is negative 1.645. This is the value that we want to compare our test statistic to. Okay, so I've got that all written out here. So you've got here, look in the body of the table for 0.05, and you're going to average it out and get negative 1.645. Now we want to compare the test statistic we got of negative 1.50 to our critical value of negative 1.645. So this is the critical region here, and our value actually is here. It's before the critical region. It's in the non-critical region or the non-rejection region. And remember, if the test statistic falls within the critical region, you reject your HO. And if the test statistic is not in the critical region, you fail to reject HO. So in this case, we're going to fail to reject HO. And again, I'm just going to draw it like a number line to make it really simplified. 1.645 was our cutoff point. And the number that we got was negative 150. This is the non-rejection region, and this is the rejection region. So we are going to fail to reject our HO. There is not sufficient evidence at the 0.05 level of significance to show the mean shearing strength of rivets is less than 925 pounds. And so then you would say that this batch of rivets is good to go onto the airplane. So I just wanted to show this again. If you've got, say, an alpha of 0.05 and your test is two-tailed, you need to divide that by 2 so that you can get it in both sides. And then if it's on the left tail, then you only do it once, and then on the right tail just once. And the left-hand side is usually going to be negative. And here again is that table showing the sign that you would have in your alternative hypothesis, and the rejection regions, two-tailed, it's both sides, left-tailed, it's the left side, and right-tailed, it's the right side. Okay, and just some practice here. Determine the critical value for a 1 mean Z test at the 5% significance level. And if it's two-tailed, then we're going to do alpha divided by 2. So 0.05 divided by 2 is equal to 0.025. Then we can do 1 minus 0.025, look in the body of the table, and we will get plus or minus 1.96. And now determine the critical value for a 1 mean Z test at the 5% significance level for left-tailed versus right-tailed. And again, we're going to use our table 2. We're going to use our 0.05. We've got 1 minus that, and then you look in the body of the table, and it will fall in between two values equally. So we take the average of those values, and you end up with negative 1.645 for the left side, and then positive 1.645 on the right side. And here are a couple more examples here. So it's really critical that you pull out your table and you actually do these. So the first one is find the critical region and values for your alternative hypothesis of mu less than 19 and alpha is equal to 0.01. So of course, in this situation here, it's left-tailed, so you know it's going to be a negative. And if we go 1 minus, I've got a pen, 1 minus 0.01, that's equal to 0.99. And you're going to look in the body of the table for 0.99. And what you'll find with that one is it's pretty close to falling in between two of them, but it's not quite there. So it will be a negative 2.33. Now this one down here is a two-tailed test. So find the critical region and values for HO is equal to 20, and then our HA is not equal to 20. When you see that not equaled sign, you know that that means it's going to be two-tailed, because we have to look on both sides. So it's two-tailed, so you take your alpha of 0.10, divide it by 2, that equals the 0.05, and then you can go 1 minus 0.05, and that ends up being 0.95, and this one falls in between two, so you take the average and it ends up being the 1.645. So again, some of these numbers you start to memorize over time. All right, now we're going to look at the p-value approach, and what you're going to find is that the p-value approach is what's used mostly in technology. So if you're doing statistics on a technology or technological program, which you most likely will be, you're going to be using the p-value approach to hypothesis testing. And what we do here is we will first evaluate how likely observation of the value obtained for the test statistic would be if the null hypothesis is true, and the P in p-value stands for probability. The p-value of a hypothesis test is the probability of getting sample data at least as inconsistent with the null hypothesis, and so supportive of the alternative hypothesis, as the sample data actually obtained. Alternatively, we can define the p-value to be the percentage of samples that are at least as inconsistent with the null hypothesis and supportive of the alternative hypothesis as the sample actually obtained. And we use the letter P to denote p-value. Now, small p-values provide evidence against the null hypothesis. Larger p-values do not. So the smaller or closer to 0 the p-value is, the stronger the evidence against the null hypothesis, and so in favor of the alternative hypothesis. Now, you guys have already done this. You just maybe don't realize you have already. I want you guys to think about in lab when we run the Shapiro-Wilk test for normality. We're always comparing the p-value to 0.05. And sometimes you'll hear the p-value of a hypothesis test referred to as the observed significance level. And so let's think about this in terms of an example. Suppose that the p-value for a hypothesis test is 0.07. So then we can reject the null hypothesis at the 10% significance level, because P then is going to be less than 0.10. But we cannot reject the null hypothesis at the 5% significance level, because P is then going to be greater than 0.05. So in fact, when you're looking at that example, the null hypothesis can be rejected at any significance level of at least 0.07 and cannot be rejected at any level less than that. So the p-value of a hypothesis test is equal to the smallest significance level at which the null hypothesis can be rejected. And this is the decision criterion for a hypothesis test using the p-value. If the p-value is less than or equal to the specified significance, reject the null hypothesis. But how do we get the p-value? And so to determine the p-value of the hypothesis test, we assume the null hypothesis is true, and then you compute a probability of observing a value of the test statistic as extreme as or more extreme than that observed. And so by extreme, it means, far from what we would expect to observe if the null hypothesis is true. Now, to determine the actual p-value, we're going to get it on technology. It's going to calculate it for us, but I'll show you guys how you can estimate it using tables. One thing I really like about statistics is that everything is super organized, and you can set everything up in a step-by-step procedure that helps us to make that decision. It's pretty black and white in terms of the steps. So when we talk about the p-value approach, let's talk about how we actually go about doing it, and it's kind of similar to the critical value. So first of all, you need to set it up. You need the setup. And what I mean there is that you need to make sure that you've got all of the sample information that you need and you're ready to run the test, because the math is actually the easiest part. Then we need to do our state our null and alternative hypothesis. This is going to help us to investigate the problem. So in the first part, we've set it up, we've described the population parameter of interest, and we, gathered all the data, whether it be a mean, a standard deviation. Then we're going to make a decision about what we're testing for. Is it less than, is it more than, or is it on two sides, a two-tailed test? Then we need to gather all of our sample evidence and calculate our test statistic, which is actually the easiest part. And then we need to calculate the p-value of the test statistic and determine whether or not the p-value is smaller than alpha, which helps us state our decision about our null hypothesis. So when calculating the p-value, assume the null hypothesis is true and compute the probability of observing a value as extreme or more extreme. Now you guys won't really be computing those, you'll be estimating them, and I'll teach you how to do that in a bit, but on the computer it will calculate a probability for you, and then we've got our results. This figure here is showing the p-value for a one mean Z test if the test was two-tailed, as shown in A, left-tailed in B, and right-tailed in C. So with the two-tailed test, the p-value equals the probability of observing a value of the test statistic, Z in this case, that is at least as large in magnitude as the value actually observed. So it's the area under the standard normal curve that lies outside the interval from negative Z to Z. Now with the left-tailed test, it's the probability of observing a value that is smaller than the actual observed value, which is the area under the standard normal curve that lies to the left. And then for the right-tailed test, it's the same thing, but it is just the area under the standard normal curve that lies to the right. Okay, so we'll do the same example as we did before, but then we will just sub out the critical value approach with the p-value approach. So, man, these Boeing 737s have a lot of issues. You guys might actually recall, I can't remember when it was, but there were about 62 passengers and crew that died on a Boeing 737 because it crashed shortly after taking off from Jakarta. This is pretty recent, and so this is only one in a whole long line of accidents. So again, let's look at our population parameter of interest is the mean shearing strength of the rivets, and we've got our null and alternative hypothesis, the same as it was before. It either equals 925 pounds or it's less than 925 pounds. All right, so we already were able to calculate the value of the test statistic when we had done it previously. We had done that before, and it ended up being negative 1.50. So what does that mean? How do we know whether to reject or accept? Well, not really accept, fail to reject, and make a decision, and we need to calculate our probability value. So one thing that really always does help is if you draw a sketch of the standard normal distribution and locate your statistic on it. As you can see, I've done below there. I've got my negative 150 on there. So using table 2, we need to determine our p-value. And I want you guys to grab out your tables and make sure that you've got it, and so that you know what you're doing. So what I'm going to do is I'm going to use my table 2, and I am going to look for the z-score of negative 1.50. And when I do that and I look at the area under the curve, it ends up being 0.0668. This is our p-value. It's super easy to find your p-value when we're using a standard normal curve. It's super easy when we're doing it with the t-table as well. It's just a little bit different. So when we get there, I'll show you guys that. But the p-value is actually just the number 0.068. And we're comparing that number to our alpha of 0.05. So we're not using this to find the number in the table, but we are using it to compare to our number here. And so 0.0668 is bigger than 0.05. So what does that mean? How would you conclude on this? And so make a decision about it. It is not less than. So do we reject or fail to reject our null hypothesis? And I want you guys to figure that out. Try to come up with the answer. So hopefully you took a pause so you could kind of evaluate your p-value compared to your alpha value. But the p-value in our case is not smaller than the significance, so we fail to reject our null hypothesis. The p-value is not small enough to indicate that the sample evidence that we have is highly unlikely in the event the null hypothesis is true. So there's not sufficient evidence at the 0.05 level of significance, or the 5% level of significance, to show that the mean shearing strength of rivets is less than 925 pounds. And we had the same decision when we did it with our critical value approach. Most of the time they will be the same. There are some times that they will not be the same as each other. So the idea behind the p-value is that we're expressing how much we believe in the null hypothesis. And so the pros of this is that it's based on a probability scale rather than a yes/no. And so the p-value can then be reported and assessed based on the situation. And finally, the biggest pro is computers will calculate it for you, and then all you have to do is compare. But the cons are that people are kind of scared of it. I don't know why, but they fear technology and they fear statistical programs. And there can be a hard choice range sometimes as well. So think about this. When the p-value is really, 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 really tiny, the null hypothesis is rejected because the sample results are pretty unlikely to be true. But when the p-value is bigger, like 0.08, there's too much probability that the data, like the sample involved, could have occurred if the HO were actually true. When the p-value is really large, the data are not at all unlikely. So there are some advantages and disadvantages to this approach. My personal view is that I will use the p-value approach every single time, and I've never seen anything in publication. If you're going to do research and get published, I've never seen anybody use a critical value approach. Okay, guys, this is some practice for you. So if the p-value is less than or equal to the significance, you reject your HO. And if the p-value is greater than the significance level, you fail to reject your HO. So I'm just going to, walk you through the first one, and then you could try the other ones on your own. So we've got a p-value of 0.014, and we have an alpha of 0.02. So what are we going to do here? Well, our p-value is less than our significance value, and so we are going to reject HO. Now try the next ones on your own. It should do reject and then fail to reject, fail to reject. All right, and here's some more practice for you guys to do. Try to calculate the p-value of each of the following here. So the first one here, you're just going to use your z-score that you get here of negative 0.85. It's left-tailed, so you know it's just the one side. But we've got a two-tailed one here, and so what you're going to have to do is you're going to look in your table for negative 1.71. And when you do that, what you'll get is 0.0436. But since it's on both sides, you have to multiply it by 2. That's the only trick here. So if you've got a two-tailed one, multiply your p-value by 2. And finally, here are some guidelines for using the p-value to assess the evidence against the null hypothesis. Essentially, the smaller your p-value, the more evidence you have against that null hypothesis.